hello everybody. So I'm Paul. Something about myself, I studied electrical engineering and then changed to information systems engineering, finishing my diploma. And to share something how I came to Sapphire, I'm like a user. I programmed several mainly one application professionally in Sapphire, and before I was working with different chips from Atmel to STM or NXP, and every time it was very annoying for me having a project with a different chip, and then I had to spend a week or so learning the new SDK or Hall. And when I almost finished my studies, I was a second engineer joining a project that was bare metal, and then my job was to integrate network and MQTT into the microcontroller, and I almost spent a week trying to do that with LVIP, but had several issues. And then I heard about Sapphire in a podcast, and I thought maybe try that out one day, and it just worked. So my experience was really smooth there, and the samples in the documentation were much nicer than a lot that I was used for the Cube STM, for example. It was quite clean and readable, so I was really convinced. And also my colleague, who was the other engineer in the project working before, he then agreed to change. And the other two engineers who later joined that project also learned Sapphire, so I never taught Sapphire, but I convinced colleagues to join. So that was my experience convincing people. But before learning Sapphire, I used FreeRTOS, and the thing that I was used there as well, that when we are managing memory and configuring our task, that the stack that we assign to a thread usually takes like the default setting 1 kilobyte, and sometimes we get in Stack Overflow. You spend some hours debugging that, and then you find out, oh, the stack is too short now, and then what do? It's not a number thing, but maybe you double it if you have the space. If you're tight of memory, maybe you add 50% or some 100 bytes. And I think one particular problem where I'm currently working at, we had a Stack Overflow that only occurred during a very specific event when we tried to update a subcomponent, and it was in the release since some versions, and we just found out when the supplier sent us a new firmware update, and the update never worked. And then we were thinking about how could we have noticed earlier, and that's what the talk basically is about. So static analysis can mean a lot of things, but usually at some point when you're developing a product for over many years and adding new features or having new variants of your products, you're adding features, and the memory just gets fuller and fuller, and at some point you have to try to optimize. And so I want to present some ways that already exist, how you can tackle then where to get information where you can cut or optimize for memory, and how we could do that in a more automatic way and raise awareness between colleagues. And so basically if you used Sapphire, maybe you know the optimization page, and when you had a Stack Overflow and analyzed it, maybe the most common way, you're analyzing the memory that you're having at the moment in the application. And so it's automatic in Sapphire. In FreeRTOS, it's a high watermark, so that you're initializing the stack with some pattern that you know, and then you see how far that pattern was overwritten. So like the memory is used to a certain point, which is painted red here, and then this happens in other tasks as well. And in Sapphire, you have this thread analyzer, which gives you in the console the log, which is quite nice, where you can see, okay, from this thread we used so much memory, and probably we triggered the worst case path, and maybe we have some memory left over here, so you can do that during runtime. But usually we don't do that, or have to do it ourselves, check it manually, and we don't do that regularly during the way I am used to working with embedded systems. So, and if we know that we are wasting maybe memory, or we had a Stack Overflow, we can configure the stack sizes, to either not cause a stack overflow anymore so that we have enough memory, or trying to free some memory by adapting the stacks that are used from Sapphire for the substack of, I don't know, Bluetooth, CAN, USB, or our user threads. But usually I think it's more like a gut thing, that you have some idea or you just double it and hope it doesn't crash. And some existing tools which can help you to make a more informed decision are listed here. The two on the right are integrated in Sapphire. The RAM and the ROM report is the command line thing, and since 2 weeks, I think the graphical version of that is also available in Sapphire. From other projects, I knew the map file viewer, where you can see the global RAM and ROM usage of files. And from Mbed OS, there was this linker explorer, which is quite nice. So there came from some inspiration from. So this is the linker explorer of Mbed OS. Mbed OS, you already said, it's quite almost dead. And here you can see, for example, the text part of the application. So the flash usually is like 64 kilobytes big. And then you can see, okay, here the Mbed OS feature importer, whatever, takes like 10% of flash. And then here you have 30% of heap. And here's some application stuff in the end, where you can see this is the which segment of memory, BSS, so RAM. And then you can also zoom in and see that. So I took some inspiration from that to also be available in Sapphire or like not Mbed OS applications. And the other version that is baked in into Sapphire already is PunCover. I don't know, did anybody of you use PunCover before? Or do you know about that? Or no, some not. So what PunCover is doing basically is taking the ELF, so it's not limited to Sapphire, but you can just throw an ELF at it and it takes the global memory usage for static RAM and stack. And if you have your build files and can integrate it in your build system, it also can tell you the stack usage, the worst case stack usage, and that can be done by some information GCC can generate out to .su files, where the stack usage of each function is, the worst case stack usage of each function is shown line by line. But we have some limitations there, since PunCover is not RTOS aware. And on the one hand, you don't know about threads there, so it's just symbols of functions, and also dynamic calls, of which quite a lot are in the Sapphire stack, but also users add their dynamic callbacks, so the analysis oftentimes misses a lot of the calls. But as a user, you're providing these callbacks, and the Sapphire ones you could maybe automate to generate out and write it to a file. So these are like the fronts where you could improve on PunCover. But like this is the PunCover as you can use it in Sapphire, if you haven't seen it. So you get like a file explorer, where you can step inside the folders and see your source files. So if you see like the kernel of Sapphire, here the init file, the init.c, uses like 3 kilobytes of static RAM and 600 bytes on the flash. And then you can see all the functions that are inside the init.c. So for example, we can take a look at the functions, and you see all the places where it's called from and that it's calling. You get the worst case stack size and the flash usage of that function, the disassembly and reference to all the functions, and the worst case stack definition. So the kernel init here says it has a worst case stack usage included in a path that is like 500 bytes on the stack. And here's a list of all the functions that are included and how much space on the stack they consume. So this is quite nice information already. But it's, if you go to you can click it on the file basis or show a list of all the symbols that is included and sort that on the stack usage. And you see some functions are quite big on the stack and consume more or less flash. But it's like just a list, so you don't, the context of the RTOS is missing. So you have to think about it yourself and explore through the symbols. And that is for what you can do to analyze your current state of the application. But as you progress during development, maybe you want to see some trends if you're improving your memory usage, or if you're staying almost the same, or and there I want to highlight a blog article from Memfault, which I really liked, where they describe how you can set up for each commit a size difference in static RAM and flash usage through the general segments that you get during build time as well. So I think you can see here like a list of all the commits and how it changed flash and RAM usage. But I think it's kind of difficult to set up. You need a database, and also it's global, so you don't know which line of code in which file changed which data structure or function. And yeah, you don't have the stack information in that. So that's about a more informed approach that you can already use to know where memory is short on your application. And yeah, basically, I want to show you now how we can improve on PunCover, and some implementations I already did. And yeah, is it really the best way to use PunCover for that? Yeah, it's already integrated in Sapphire and has a abstract representation of all the call graph in your application. It has maybe some edges and bugs still, but anyway, I think it was an easy point to start and where to improve. And it's already giving a lot of valuable context to the engineer. So that's why I think it's the best open choice I found where we can improve. And so I added more options to PunCover. These are like the basic ones. You usually just need the ELF file to parse the ELF and see global memory usage, and then the build directory to get the stack usage of the stack usage files. You need to change the, if you're just using GCC, the -f stack usage option in Sapphire, you have a kconfig for that. And then the options I added, for example, is a list of all the threads that I'm interested in. So here's like a list of 5 threads, and it's separated so that you can use it also in the command line by 3 dots with the size of the stack, so 1 kilobyte for the 4 of them, and here it's like 700 bytes. And yeah, here down below you have 2 more options where you can say, hey, I want a warning from PunCover if I'm just 100 bytes short of having a stack overflow, and I want an error during the analysis if a stack exceeds the stack that we configured as users. So that can be already quite useful in CI. It's work in progress. I don't have the example configurations yet, but the basic idea is that you run PunCover, and then you get either one code for a warning, you're almost statically close to a stack overflow, or an error that you're certainly violating your own memory requirements that you set for your stack. So the idea is that in GitHub CI markup, it looks something like this, that you run PunCover, you allow the warning that you're close to fail so that you get a yellow warning, and if it's another exit code than 0, it will throw you an error. So it's still work in progress, but I hope I can give you an example for GitLab and GitHub action soon. And then so that you don't have to set up a database in the background, it can all be written to a file so that you can compare the informations of 2 builds. And yeah, so that's the idea behind that. And for dynamic calls, here's a manual example for now where the implementation of the Sapphire CAN. So I used as an example here CAN activity, which is like a CAN sniffer, which is built on Sapphire, which uses USB and CAN. And for the CAN boss stack in Sapphire, there's like callbacks from the implementation to the real CAN driver, the mCAN driver. And so there's an example of 2 dynamic callbacks that I added here, which are then also analyzed in the static analysis of your application. And the last thing, that it was really hard to extend PunCover because it's like you do the analysis and then the results are loaded into RAM and it shows you the dynamic web application. So adding it always did a reanalysis, and it took for some firmware quite a while. So I wanted to export the data and separate the analysis part and the representation. So I did a JSON export. I'm not really happy about the data structure. I think we could find a better schematic for that, but basically you get for each symbol, if it's a function or a variable, where it's located in memory, which is the size in flash, from which file it comes, which is the name, the disassembly of the function, and in which worst call tree it's included from the callees and the callers. So if you can add up these three numbers, you know the worst stack usage of the function, if it's using floating point stuff. And this is for functions. And for variables, you're just getting the size and where it's located. I think maybe type information would be nice here as well. But it's all kind of hacky, and just to make a minimal demo for you at the moment. So the representation part, I sourced that out to a web application. And here's some screenshots, and then I will show you a live demo later. So you can load various JSONs exported from Puncover, and then you can, for code reviews, see, for example, the difference which changed during two states of the analysis. For example, here we have the Hello World Zephyr from 2.7 and 3.7, and you can see, okay, it's using less, no, it's using more flash now. That's the way of the comparison. So you 10 kilobytes more into flash usage if you upgrade, and you need 5 kilobytes more of RAM. And for the background thread and the ready thread, also it grew a little, and here's like the difference of all the symbols that changed in memory. So that can be used between colleagues during a code review, so that you can view which changes in the C code are affecting the memory footprint of your application in the end. And to see like the maximal stack usage over a set of releases, I added a page so that, for example, here for 3 releases, you see like the tendency, if it's going up or down. And for exploring the file system as before, I added the sunburst chart, similar as in the linker report, so that you can see the hierarchical thing without, like in Puncover, clicking through all the folders. You see all the layers at once. So I think that's nice to get a feeling also. If you're new to a project, you can see immediately how are the kernels consuming 10 kilobytes, and maybe this functionality of your firmware is taking up so much logic inside of your program text, and it's consuming so much memory for data analysis or whatever. And then the same trend data for the thread usage is here added on a more detailed view, where you can see for each thread how the worst call stack changed for all the functions. So you see here over 4 versions the whole worst call tree for the thread and how that changed. You can see like this function here grew by something between these 2 releases. And also this is a thing that we were particularly interested in the group where I'm working with. We integrated some C++ standard lib functions. We're really surprised that they're allocating, and we didn't know that. And so there was like discussion in the team, how can we drive that down? And we wanted to watch like standard sort or something that's doing hidden allocation in our firmware. So here you can see with a tendency, okay, during the last release, we even increased dynamic allocations a little. Usually you don't trigger that, hopefully, so that we don't get memory fragmentation, but yeah. You can add other metrics that you're interested in as a team for like coding guidelines or trends about your firmware that you're interested in, quite easily comparing 2 builds or a series of builds all at once. And here's the interactive demo. So that's the welcome page. So you can either upload, the upload I think it's not working at the moment. The way I usually used was by adding a link. And here I have some examples I can load. So for example, the connectivity releases. And to browse them, you can then select the version and you get what I already showed you. For example, if you want to know connectivity, like the user part, the source directory, you can see that like some USB functions are quite heavy. And here's the sources directory where, for example, the led.c file takes like 1.6 kilobytes. This is for the flash usage. And here we have the static RAM usage, which is heavy also on buffers that you add as a user. Or here from Sapphire, you can see it's like the heap is quite big with 6 kilobytes, and the kernel has 5 kilobytes of RAM usage already out of the box. So you get a feeling also for the memory footprint of your applications. And like comparing the releases, for example, we can compare release 1.1 to 1.0, and there we can see the stats changed a little, but not that dramatically. Then you can also, here you see just the symbols that changed in size, and the variables, you see there's a lot of noise here from Sapphire. So I hope with some generation of configuration we can clean that up a little. And then you get a list of functions here. You can also view that like in the old pan cover, that you see like callers, callees, the size and the disassembly, and the table with the worst stack path. And for the threads, you can see then how each stack's worst call path changed. I think in the latest version, the LED thread was removed, and so it has quite a drop here. For other functions, you can see that here the colors are not easiest to identify. I think here something in the logging increased a little in size. So so we increased some bytes here on the stack usage, and then you can see like the table of all the threads here as well. And if you're short on memory and you want to optimize for that, it's quite useful, I think, or just to get into the application or understand which changes in code affect memory footprint in the end. And I think the trends page is the last one. It's not so interesting with connectivity. It's stayed quite stable. And here the LED thread was dropped, and here the USB thread increased a little in usage, but it's 1 kilobyte, so we're like 200 or almost 400 or 500 bytes away from that. But if development proceeds, it's a good way to see how your changes affected memory footprint and performance. And basically this was all about memory so far. Yesterday we already heard the talk about worst case execution time. I think this would be like the most interesting thing to add. And I just started reading this book from Peter Gleaver, but from the talk from yesterday, Titan, I saw that two of the controllers supported in Titan are also in the Sapphire, supported in Sapphire, like the one from Infineon and the other ESP, the RISC-V one. So maybe we can try to glue Titan also to static analysis. And there's a lot of small issues still with pan cover and all my extensions as well. So it's more like a demo, but I think it would help that you as an engineer have a better feeling and understanding for memory usage in the stacks you're using. And some, like here especially, like thinking about worst case memory usage, you could say also you should better view it in runtime because it might be different, and it's true. But if you have this kind of variety that you sometimes had, example here for connectivity, it's over 40 devices, over 40 different build targets. It's kind of difficult to build a big hardware in the loop test, especially if time is short and you want still some confidence in that you don't get a stack overflow in the field. So static analysis is just cheap and fast. If you have time to set up a hardware in the loop, it might be the best option to measure memory or stack usage there. But static analysis is just cheaper and faster if you want a head start there. And I think also for Sapphire development in general, it can be interesting to maybe export this kind of memory footprint so that the Sapphire project itself can see how the memory usage of subsystems, for example, change over the releases. If in the project in Sapphire we want to optimize for memory, that might also a nice way to see for hotspots where we can cut some memory. And especially because the default stack sizes are the same for a lot of targets. For some, the usage might be higher or lower, so it has to work for all of them. This can help in some ways to adapt the stacks for different targets as well. And just for a motivational outcome, how would I like to see it integrated maybe in some way? Because usually when you compile, you're getting like the memory footprint of your flash and RAM. But if you can integrate it maybe in the build system of Sapphire, and static analysis catches a stack overflow, maybe one could get in the future like a warning, hey, your host communication thread had a stack overflow, and then it shows you even the call path where it would happen, so that you don't start testing and then get a surprise in the field, hey, why it's not working, and then you dig hours and days into debugging that, and then you find out stack overflow at some point. And if you just during linking the memory is not enough, you get an error already, but the stack usage, you're just assuming it works until it doesn't, and it's quite a nasty surprise, so it would be maybe nice to integrate it into the build system in the future. And concerning worst case execution time, if one could one day maybe have that as well for a lot of targets, it would be nice to also, for a cycle in the thread, show that to the user during build, so that we can also do some CPU time budgeting. I mean, it's quite difficult to know how often a task used and gets triggered, but at least you get some number. Maybe you can also add kconfigs for each thread. What would be your worst case that you're accepting for your application, or something that you get some compile time feedback of that as well. But I think that you get the global overview of memory is quite nice. It gives you a feeling for a tendency, but just at that point. But keeping an eye on memory is, has a lot of more details that maybe this extensions to Puncover can help identify engineers in the future. So if you're interested, the fork of Puncover with the new features is here. The separate repository for exploring the Puncover export is here, and like an interactive example is listed here, and the presentation slides are linked as well. So that was it. Yeah.
Thank you, Paul. Very interesting talk. I guess there are a couple of questions, I would imagine. Yes.
Thank you. I am interested in the static analysis part. And so how do you deal with the unknowns, like if recursion is used, and given that you do binary code analysis, I guess there is a number of instruction sets that you are covering, and not all possible instruction sets, right? So what are the limitations of this binary analysis?
So I think Puncover is currently only working for ARM Cortex-M and RISC-V, if I'm not wrong. And there's a lot of holes inside, for example, symbols that are from a linked library, for example, where you don't have the source. GCC is not generating the stack usage for you there. So I don't know if I can find an example, maybe. Yeah, you can see it here. Like for the stack usage, I just put a question mark for now there.
Okay.
So the analysis is definitely not complete. It's more like a demo. But for linking dynamic libraries or static libraries into where you don't have the sources, it's a limitation. Certainly in Puncover, there's also path resolution issues. So sometimes it does not find the correct source file. So it's more like a rough estimate with some edges to it. So you cannot take it 100%, but it's more like a demo at the moment.
I guess that there is some algorithm to detect recursion, right?
Right, sorry about that.
Yeah.
GCC gives you 3 labels. So you either have a bounded stack usage, a static stack usage, a static but bounded usage, or a dynamic. And so GCC tells you, okay, that is probably the stack usage, and if it's static and static bounded, you can be sure. But if it's dynamic, then it tells you basically you cannot know, because maybe it includes recursion or some unknown.
Okay, so the analysis is done inside GCC?
Yeah.
Okay, thank you.
So there's a paper from AdaCore from 10, 15 years ago where they implemented that and merged it to GCC, and that's what Puncover was using internally.
Any other questions? maybe I have one. When I was looking at this, have you thought about, because what we do in development typically is we compile applications with different configuration settings, put that in a sample YAML or in a test case YAML, so we try to integrate that with Twister. That would be very nice to kind of see then, if you switch that on or off, what the deltas would look like. Like, have you thought about integrating that with Twister, or is it maybe already integrated because Pan covered? No, okay.
No, but it sounds like an interesting idea.
Yes, so PR is welcome, I would
Like
imagine.
automation and like extracting configurations from Sapphire, I think it would be very fruitful so that you get a better analysis.
Yeah.
I don't know how that could work, but yeah.
No, we can collaborate on that one. That would be interesting. Very good. And the other question, you mentioned GCC. Do you know if there's also tooling available for LLVM?
Not sure if it's the
Or does
minus
anyone
F
else
stack
know?
usage is available in LLVM.
Because typically we always think that LLVM is the more modern tool chain for all of these things.
Yeah, I just saw that Pancover uses this flag in
GCC.
GCC, and that Ada Core published an open paper about that, so no idea about LLVM at the moment.
Okay, thank you. All right, if there are no more questions, thank you again, Paul. Very good talk, liked it. And we give the stage to Roberto.
Yeah, and there's a lot of universities here, so if you have students who maybe search a thesis and want to advance static memory analysis for memory or runtime, I think that's quite a nice topic, and it's like not so heavy to get into it, so maybe you can propose that.